Hello students, I am Sachitrakar. Welcome to Cars Physics. We are continuing work, power and energy. In this lecture we will discuss potential energy. So what is concept of potential energy and how to calculate potential energy and some fundamental numericals on the basis of formula. Okay. So let's start from energy. We'll discuss potential energy, but let's discuss first what's meant by energy. So, what is energy? Energy is fundamentally, basically, energy is defined as the ability of doing work. Okay, or you may say capacity of doing work. So energy is ability of doing work or capacity of doing work. Means if energy is spent, then work is done. Energy is ability or capacity of doing work. Means if we have energy, we can do work. Okay. So work can be applied mechanically by applying force. Okay. Suppose a block is placed on the surface and I will push or pull the block. Then work is done by the applied force. Or work can be done by opposing force. Again we have discussed work done by conservative force, work done by non-conservative force. Okay, positive work, negative work, no work. So we have already completed the discussion on work. Okay, now energy. Energy is ability or capacity of doing work. It means at the cost of energy, work is done. So at the cost of energy or at the exchange of energy, work is done. Okay. So work is a form of energy. Okay. Work is a form of energy means if energy is supplied, if energy is spent, then work is done. And if work is done, if energy is spent, then equivalent amount of work is done. So when it is true, if energy is spent, then equivalent amount of work is done. Equivalent amount of work is done. It means there is no loss of energy. If we assume that total energy spent is converted to work, there is no loss of energy. Then it is possible. Amount of energy spent is equal to amount of work produced. Thus we may, in general way, considering there is no loss of energy, if energy is spent, then equivalent amount of work done and vice versa. It means if work is done, then equivalent amount of energy is produced. So work and energy are interconversible. If energy is spent, equivalent amount of work is done. Okay. If work is done, then equivalent amount of energy is produced. Thus, work and energy are interconversible. Okay. So again, from this discussion, it is clear that units and dimensions of energy are same as work. Units and dimensions of energy are same as work, and as you know, units. Absolute unit. Number one, in any case, absolute unit of work is Newton meter, joule. In CGS, absolute unit is force into displacement. Dyne centimeter, that's equals to arc. In FPS, force is pound. Okay. Units of force is pound in FPS general. Okay, as you know, but engineering, in FPS engineering system, it's different. Okay, pound and units of length or displacement is foot, means it is foot pound. Then second type of unit is gravitational unit. Gravitational unit. Again in M case, force into displacement, force is kg force or kg weight. Displacement is meter, that's equals to 1 kg meter, and as we know, 1 kg meter is equal to 9.8 joule. That's the simple thing to convert gravitational units to absolute unit. To convert gravitational unit to absolute unit, just multiply value of acceleration due to gravity. Value of g means 9.8 in m case is multiplied, then kg meter means gravitational unit is converted to absolute unit, and in FPS, in CGS, it's equals to units of force is gram weight or gram force, displacement is centimeter, and it is 1 gram centimeter, and again 1 gram centimeter is equal to value of acceleration due to gravity in CGS is 980 and 980 arc. Okay, and similarly in FPS, units of force is pound. You may directly convert it 1 pound weight, kg weight, gram weight, pound weight, and simple multiply value of acceleration due to gravity in FPS. In M case, value of acceleration due to gravity is 9.8. In CGS, the value is 980. And in FPS, the value of 32 foot per second square, and it is 32 foot pound. And dimensional formula you know, force into length, too simple. Okay, so this is about fundamental discussion of energy. Work and energy are interconversible. When work is done, equivalent amount of energy is produced. And when energy is spent, equivalent amount of work is done. Thus, work and energy are interconversible. Again, capacity of doing work is energy. Capacity of doing work is energy. We will discuss potential energy, but first have idea on energy. Capacity of doing work or ability of doing work is called as energy. Then how many types of energy are there? Too basic. How many types of energy are there? Different types of energy. There are different type of energy depending upon nature of work. There are different types of energy. So how many types of energy? Different types of energy. Okay, and different types of energy depending upon nature of work. Means what is nature of work? Depending upon nature of work, energy of different types. Suppose what we have already discussed now itself. By applying a force, a body is displaced. So this force is mechanical force. You may apply the force by yourself, or you may employ a machine to apply some force on a body so as to displace it. Okay, that is mechanical force. On the body, mechanical force acts. So body executes some displacement. So if mechanical energy is spent, then the energy is mechanical energy. Nature of work is mechanical work, so energy produced is mechanical energy. And similarly, under electrostatic force, there is electrical energy. Electrical work, sorry. If electrical work is done, then electrical energy is produced. And in gravitational field, gravitational energy. Different types of energy, mechanical energy, electrical energy, gravitational energy, thermodynamical energy, nuclear energy, so many types of energy are there. But what type of energy? What is the name of energy? That depends upon nature of work. Okay, electrical work, electrical energy. Okay, mechanical work, mechanical energy, thermodynamical work, thermodynamical energy, and so on. Okay, so this is about energy. Then we go to gravitation. After completion of some subjects, some chapters, and here we are considering on mechanical energy. Mechanical energy. Okay. Then mechanical energy is of two types: potential energy, and kinetic energy. Mechanical energy. Mechanical energy, potential energy, and kinetic energy. But in previous lectures, we have discussed how potential energy can be defined. Potential energy, we have discussed conservative work done by conservative force and work done by non-conservative force. So work done by conservative force defines change in potential energy. Okay, work done by conservative force defines change in potential energy. Work done by non-conservative force, I am writing, work done by conservative force defines potential energy. Okay. Similarly, work done by non-conservative force not only non-conservative force, work done by conservative force, or you may write in simpler way, work done by all forces is equal to change in kinetic energy. But in general we say work done by non-conservative force defines kinetic energy, but work done by all forces means conservative force. Non-conservative force. Internal force. external force, etc. Whatever be the name of force, work done by all forces is equal to change in kinetic energy. Of course, we have just discussed work done by conservative force defines potential energy. Work done by non-conservative force. Suppose I am writing an example. Work done by frictional force. Frictional force is non-conservative force is equal to change in kinetic energy, and in this chapter we may take help of frictional force to define or to find change in kinetic energy. Okay. So work done by non-conservative force defines kinetic energy, and total change in kinetic energy is equal to work done by all forces. All forces means conservative, non-conservative, internal, external, whatever be the force. Work done by all forces is equal to change in kinetic energy. This is fundamental discussion, and now our discussion is potential energy. Work done by conservative force defines potential energy, and example of conservative force are, as we have discussed, gravitational force, electrostatic force, gravitational force, electrostatic force. We have discussed this total concept, work done by conservative force and work done by non-conservative force, and the characteristics of work done by conservative force and characteristics of work done by non-conservative force. Those who have not gone through the lecture, you may go through just previous lecture, lecture number 3. Lecture number 3, Cars Physics, Work Power Energy. You go through it. We have discussed the complete concept of work done by conservative force and work done by non-conservative force. First go through it, then it will be very easier. Fine. Then about potential energy, we will discuss in brief. Okay, potential energy. Work done by conservative force defines potential energy, and examples of conservative force we know. Then how to calculate work done? Work is equal to, suppose I am writing dW, total work, Fs. S is displacement, you may take x along x axis, y along y axis. Okay, work is equal to Fs, and change in potential energy. Potential energy delta I is equal to negative of work done by conservative force. Very important to calculate change in potential energy delta I. We can take negative of work done by conservative force. So I have written the heading potential energy, but I am writing here the formula for change in potential energy. Why? Because in physics there is no definition of potential energy. Physics doesn't define potential energy, but change in potential energy. In physics, we do get the formula or definition of change in potential energy, not potential energy. Okay. So we can't calculate directly potential energy. We can calculate change in potential energy. Then what is fundamental definition of there is in physics there is method of calculating change in potential energy, and this is the method. Change in potential energy is a negative of work done by conservative force, means non-conservative force doesn't define work done by non-conservative force, doesn't define change in potential energy. But what is potential energy? Yes, we can define potential energy. See, suppose delta E means change in potential energy, means final potential energy minus initial potential energy. If initial potential energy is 0, suppose initial potential energy 0, then delta U is equal to final potential energy, which is termed as potential energy. We may say it is potential energy because initial potential energy is 0. U final minus 0 is U final. So if initial potential energy, if initial potential energy is taken as 0, then final potential energy may be named as potential energy. Then what is fundamental definition of potential energy? Directly in physics, there is no definition of potential energy, but definition of change in potential energy. But in basic way, we can define potential energy. It is energy possessed due to position in a field or due to change in configuration. Okay. Or you may say change in potential energy, same thing, but change in potential energy becomes final, equals to final potential energy if initial potential energy is 0. So what the definition means? It is potential energy or change in potential energy. If initial potential energy is 0, then we can define this. It is energy possessed due to position in a field or due to change in configuration. Let's discuss this first. Due to position in a field, suppose a body is in gravitational field. Suppose a body is in gravitational field, then the body possesses gravitational potential energy. Then how potential energy do you say? See, suppose this is gravitational field left. Gravitational field, the effect of gravitational field is up to infinity. Okay, a body is taken from infinity to a given position. Body is taken from infinity to a given position in the gravitational field, and here initial potential energy is 0, but at infinity there is no effect of gravitational force, so work is 0 at infinity, so energy is 0. And the body is brought to this position here. This is final potential energy, and work done is equal to negative of work done is equal to change in potential energy, U final minus U initial, but here U final is 0, so negative of work done is equal to U final is equal to negative work done by gravitational force, means negative of work done by conservative force. Means to get potential energy, we have to take initial potential energy 0. This is also change in potential energy. Only U final. This is also change in potential energy because this is equals to U final minus 0 is equal to negative of work done by gravitational force. This is also change in potential energy. So initial potential energy is taken as 0, so that final potential energy is equals to negative of work done by gravitational force. Similarly, suppose this is an electric field. You'll study it in 12th. So, this is an electric field produced by a charge. And at infinity, electric force is 0 or electrostatic force is 0. So, if force is 0, then work is 0, then potential energy of a charge particle outside of the field produced by another charge. This charge may be plus or minus q, and here there is another charge. So, potential energy of this charge q, small q, is 0, because beyond the field, potential energy is 0, because electrostatic force is 0. The charge is brought from infinity to this point. So, at this point, potential energy is final. Since initial potential energy is 0, so final potential energy is equal to negative of work done by electrostatic force. So, this is termed as potential energy at a given position. But practically it is change in potential energy. We say potential energy, it's okay. But practically it is change in potential energy. Is it clear? So, potential energy is energy possessed due to position in a field. A body is present in a gravitational field, it has gravitational potential energy. A charge particle is brought to a given position in the electric field from infinity. Then the charge particle at this position has electric potential energy. And as you know, in atomic structure, electrons are revolving around nucleus. Then the electrons are in the field of nucleus. Okay, thus the electrons are nuclear potential energy. Okay, so there are different forms of energy due to position in a field. So, in accordance with the name of field, potential energy are named so. So, potential energy is energy possessed due to position in a field or due to change in configuration. You just see. Suppose this is the natural length of a spring. Now, a deforming force is applied so that the spring elongates through x. Okay. Then here change in potential energy is half k x square minus 0, that's equals to half k x square. Or if the string is elongated from x1 to x2, then potential energy is half k x2 square minus x1 square. So this is the case where configuration changes. Or you simply think, this is a rubber cord. In very simplest way, I am holding the rubber cord here. Now, the deforming force is applied and the rubber cord is pulled so as to stretch it a little. The rubber cord is pulled so as to stretch it. When the rubber cord is stretched, then molecular separation changes. So we do say it change in configuration. Thus potential energy is energy possessed by a particle or by a body due to position in a field or due to change in configuration. But practically, keep it in mind, we are not finding potential energy, we are finding change in potential energy. In physics, there is no particular definition of potential energy, but physics defines change in potential energy. If initial potential energy is zero, then final potential energy may be termed as potential energy. But practically we are finding change in potential energy, and this is the way of calculation. Change in potential energy means delta U means final potential energy minus initial potential energy, that's equals to negative of work done by conservative force. Negative of work done by conservative force. Okay, and you know the examples of conservative force we have already discussed in just previous lecture, in lecture number 3. Okay, this is about potential energy and we are discussing mechanical energy. Suppose we have to find expression for potential energy. This is basic thing, means derivations are not required. For your understanding, I am doing the derivation. See, suppose this is a body of mass. The body is on the surface of earth. The body is on the surface of earth. Means this level of the body is called as datum level. Datum level where potential energy U1 is equal to 0. Because no work is done, no mechanical work is done to put the body, to place the body on the surface of earth. The body is initially on the surface of earth. No mechanical work is done to put the body, to place the body on the surface of earth. Thus initial potential energy is 0 and this is called as datum level on the surface of earth. Now, what do we know? Change in potential energy is equal to negative of work done by conservative force. By conservative force. Okay. Negative of work done by conservative force, and as we know, delta U is equal to F dot S. Okay. And in simplest way, you may say it du for small change in potential energy. If this is du, then this is F dot ds. Okay, F dot ds. But change in potential energy is a negative of work done by conservative force. To get total change in potential energy, we have to integrate du initial to final, that's equals to minus F dot ds. Limit is from, suppose limit from S1 initial position to final position. This is the way how to calculate change in potential energy. du is small change in potential energy, delta U is total change in potential energy. Okay, initially the body is on the surface of earth and this is datum level. Here initial potential energy 0, and as you know, gravitational force acts on the body in vertical downward direction. So we are going to find mechanical potential energy, but force due to gravity, and mechanical potential energy on the surface of earth is 0, because no work is done to keep the body on the surface of earth, no mechanical work is done. But if you consider purely gravitational force, then on the surface of earth potential energy, you may find change in potential energy. I am just showing you gravitational potential energy. See, this is earth, this is center of earth, this is radius of earth. So at center, initial potential energy is 0. On the surface, potential energy is minus g. Mass of earth is m. Suppose here a body is placed m, minus g, m, mass of earth into mass of body is m divided by r. Okay. This is potential energy. Then potential energy, change in potential energy is equal to negative of work done. Okay. So this is quantity, magnitude of potential energy minus Jm by r on the surface of earth. On the surface of earth, this is gravitational potential energy. Okay, we'll go through it in later stage. But here mechanical potential energy is 0, but force is due to gravity, gravitational force. So gravity and gravitation, there is a small difference. Gravity is pull due to planet, or force of attraction due to planet up to a certain height. Okay, we'll discuss it in brief. Okay. Now gravitational force is acting on the body mg in vertically downward direction. Let the body is to be taken to a given position. This position A, this position B, and this displacement is h in upward direction. Displacement is h in upward direction. C. Force is acting in downward direction, displacement in upward direction. So what we have taken? Change in potential energy is negative of work done by conservative force. So integration of change in potential energy U initial to U final is equal to minus integration of F dot dH. Suppose initially the body is taken in upward direction through a small displacement dh, okay, in upward direction. F dot dh, so this is U, limit varies from U initial to U final, minus integration of F dh cos 180. See, direction of force, direction of displacement are in opposite direction. So angle is 180, means limit varies from 0 to h. So this is U final minus U initial is equal to minus, again, integration 0 to h, force is mg, dh cos 180 is minus 1, and U final minus U initial is 0, and that is 0. Then this is minus becomes plus mg, bring it outside, then integration of dh is h, and limit varies from 0 to h, and finally U final minus 0 means change in potential energy is equal to mg into h minus 0. So U final minus U initial is equal to mgh. So this is potential energy at this position, mgh, because initial potential energy is 0. So final potential energy at B means potential energy at B is mgh. This is termed as mechanical potential energy, also called as gravitational potential energy, because force of gravity is considered. Okay. Then suppose I am showing you, this is formula for potential energy. mgh, come to the previous case. This is position A. The body is directly taken to a position B through a height h, and potential energy is mgh. Suppose the body is taken from A dash position to B along this path. Suppose the body is taken, this is path 1, this is path 2. Suppose the body is taken along this path to body B, this is path 3. And as we have discussed, work done by conservative force is independent of path. What? Yes, in just previous lecture we have discussed, work done by conservative force is independent of path. So whatever be the path, so work is independent of path, so work is set along all paths. So in every case change in potential energy will mgh, because force in vertically downward direction, and from A to B displacement is vertically upward direction. Work is independent of path. Okay, very important, work is independent of path. Suppose initially this is vacuum, potential energy is 0, this is a height, let h1, a body is at a height h1, then it is taken to another position, to this position A, this position B, this is the initial position and this is final position. So this height is h2 and this height is h1. Then initial potential energy, in this case A is initial point, initial potential energy is mgh1 and this is final position, final potential energy is mgh2. Then change in potential energy delta U is equal to U final minus U initial. So mgh2 minus mgh1, it comes mg into h2 minus h1. So difference in height, if h2 minus h1 is taken as h, then it will come mgh. Okay. And work is equal to minus mg into h2 minus h1, work done by conservative force. And potential energy is negative of work done by conservative force. Okay. These are fundamental discussions. Let's have some fundamental numericals on the basis of our discussion. Change in potential energy. Again, I am writing the formula. Change in potential energy is equal to negative of work done by conservative force. Conservative force, or in if you consider small change in potential energy, this is equals to minus U initial, U final minus work done by conservative force dot displacement ds, and limit varies from s1 to s2, whatever will. If you take the displacement along x-axis x1 to x2, if you in a vertical displacement h1 to h2. Okay. So this is our formula. In first case, see the simplest example. Suppose a stick of length and mass m is placed. Number one, the stick is placed like this in a vertical position. This is ground, means datum and this is another position, this is ground. This is placed like this. The same stick is placed like this. Oh, same stick is placed like this. Okay. Length of stick is m and mass is m. Then this is position 1, this is position 2. Then how to calculate potential energy in these two cases? So you just see the uniform. Again I am writing an uniform stick. Uniform means cross-sectional area is same everywhere and material, nature of material is also same. Means uniform stick means distribution of mass. Uniform. Distribution of mass is uniform, so that the stick is uniform. And in later stage you will study in 12th physics, that is uniformly charged body. So charge is distributed equally or uniformly. Here mass is distributed equally or uniformly. Distribution of mass is uniform. And we will discuss it. If mass is distributed equally or uniformly for a regular body, a cylindrical body, a spherical body, a cubical body, if mass is distributed uniformly, then center of mass is at geometric center, means total mass is effective at geometric center if the body is uniform, and cylindrical stick we have taken, then it is uniform, then total mass is at geometric center. Total mass is at geometric center, and length is L, means this total mass is concentrated at a height L by 2, vertical distance L by 2 from the surface of earth, and in this case here u initially 0, at this position u final minus u initial is equal to final potential energies m g h, and initial potential energy is 0, so u final minus 0 is equal to m g, in place of h we can write L by 2. So potential energy at this position at the center of rod, we have to take center of rod because mass is distributed uniformly, that's equals to mg L by 2. Here also total mass is at center of the stick, and here there is total mass concentrated, and this length is again L by 2, and this is the vertical height from the surface of earth. As we have discussed, the force due to gravity is in vertically downward and displacement is in vertically upward. So in this case here u initially 0, at this position u final, and u final minus u initial. Here u final is again mg, u initially 0, so u final minus 0 is equal to mghc. This length is L by 2. Oh, I have not given the angle. Let angle is theta. Any angle you may take. This angle is theta and this angle is 90. Then h is equal to L by 2 sin theta. This is L by 2 cos theta. This is L by 2 sin theta. This angle is 90. So in place of h we can write L by 2 sin theta. So finally u final minus initial is 0, mgl by 2 into sin theta. L by 2 sin theta. Fine. The next question. See. Chain. Suppose an uniform chain. Again mass distribution is equal, an uniform chain of length L and mass M. Uniform of length L and mass M is lying on a table top. Is lying on a tabletop such that 1/5 of its length overhanging at the edge of table. Then we have to calculate work done, work done in pulling the overhanging part onto the table. Very simple, just think. This is surface of a tabletop. And an uniform chain is lying on the table, and 1/5 of chain is overhanging. 1/5 of length of chain is overhanging. Means if total length is L, this overhanging part, length of overhanging part is L by 5. L by 5. Okay. Then chain is uniform. For length L, mass is M. Then for one length, for unit length, mass is M by 5. Then M by L is linear mass density. Means mass per unit length, linear mass density per length L by 5. L by 5, mass is equal to M by L into L by 5, that's equals to M by 5. Then we have to pull this overhanging part onto the table. Then again the similar thing, total mass of this overhanging part, this is total mass, let's take small m, is at a distance, let this distance is h and h is equal to half of L by 5 because this length is, chain is uniform, total length is L by 5, so center of mass of this overhanging part is at geometric center, so the height which is to be raised means this mass is raised to a height of L by 10. Of L by 10. Okay. Then we may write the gain in potential energy. Gain in potential energy because if this mass goes up, if the mass goes up, then height increases. Potential energy directly proportional to height means there is gain in potential energy. Then gain in potential energy, let's take delta I. Let's take delta I, this is initial position. Here, initial potential energy is 0. Okay, this is initial position. The height from the ground is not given, we have to take this is static. This is static. From this position, the total chain is taken to the top of table means the mass of the overhanging part is taken to the table. Okay. Then delta U means final potential energy minus initial potential energy. Here initial potential energy is 0 at this position. So that's equals to M, mass of this overhanging part, GH. Then M is mass is M by 5 into G, H is L by 10. Then change in potential energy is mgl divided by 50. mgl by 50, this is change in potential energy and work is equal to mgl by 50. Work done by applied force. What is work done in pulling the overhanging part means applied force. This is not work done due to conservative force. This is applied force. Then applied force does positive work. For conservative work, this may be taken as a negative, minus mgl by 50. Okay, next. Another beautiful question. We'll enjoy it. Fine. Just think, I am not writing the question. Suppose this is a rod, uniform rod. This is an uniform rod. Total length of the rod, this is the support from which the rod is suspended. Total length of the rod is L. Total length of the rod is L. Let the rod is rotated and brought to a new position from position A to position B. Okay. The rod is rotated to a new position B and held here. Okay. Then the angle through which the rod is taken to position B, let 60 degree, this angle is theta. This angle is theta. Theta is equal to 60 degree. Whatever may be given, 30 degree, 60 degree, 45 degree, whatever be given. So this support is O. Then we have to find gaining potential energy. See, the rod is rotated in upward direction. This is also in upward direction. Then potential energy is gained by the center of mass. Then about center of mass, it is at center of the rod, geometric center of the rod. Let's take this position is G, and this total mass is taken to a new position. Let this position is J dash. This position is J dash, and this angle is 60 degree. Okay, or I am writing here theta. Theta is 60 degree. Okay. Then what is gain in potential energy? See, first take this is datum position, and the center of mass is taken to this position. Means this is the height through which the center of mass is raised from position G to position J dash. Okay. So total length of the rod is L, and obviously this length is L by 2, and also this length is L by 2. Then we have to first get, name this position, this is A. Then OA is height through which the center of mass is raised up. Then we have to find OA, and OA is equal to, I have taken this position A, like this is P, this is Q. Okay. Then OA is equal to OG minus AG. OG minus OA, sorry. We have to find AG. AG is equal to, height is equal to, sorry, this is AG. AG is equal to height, and AG is equal to OG minus OA. See, this angle is a 90 degree. This angle is a 90 degree. This length is L by 2. And obviously, OA is equal to OG cos theta. Cos theta, this is OG. Sorry, OG dash cos theta, this is OG dash, this is OA. OA is equal to OG dash cos theta. Theta is 60 degree, and OA is equal to OG dash, means L by 2. Cos 60 is 1 by 2, and that's equals to L by 4. That's equals to L by 4. Suppose another data you may take. Let length of rod is 1 meter, 2 meter, and mass is equal to 1 kg. Any data you can take. I am taking variable, but data you may use. So this is L by 4, and L is equal to 2. 2 by 4 is equal to 1 by 2 meter. It okay. Then gain in kinetic energy, gain in potential energy, that's equals to delta I. Here potential energy is 0, and here potential energy is final. This is initial, this is final. This is initial, this is final. Then change in potential energy in simplest way. You may write mgh, because height through which the center of mass is raised is h, then mgh, and mass is 1 kg. In place of g, let's take 9.8 meter per second square, and height, OAG is height. This is OA. Okay. AG is equal to OG. OG is L by 2. This length is L by 2. L by 2 minus OA. OA is 1 by 2. Again, L is 2. 2 by 2 minus 1 by 2. Again, 1 by 2 meter. 1 by 2 meter. L is 2 meter. 2 by 2 is 1. 1 minus 1 by 2 is 1 by 2. Okay. Then this is AG. So H is equal to 1 by 2 meter. So H is 1 by 2. So 9.8 divided by 2. So this answer is 4.9 joule. So let's check it. AG is equal to OG minus OA. OG is L by 2. Okay. OG is L by 2 into 1 by 2 L by 2. O. L by O in variable form, this is L by 2. OA, sorry. OA is equal to OG dash cos theta, it's right. OG dash is equal to L by 2, cos 60, theta is 61 by 2, right. L by 2, then answer is 4.9 joule. Okay. Then some one or two question only, and important question also. In previous lecture we have discussed how to check the force is conservative or not. You may apply this. A conservative force, I am writing like this, a conservative force, FCF, conservative force. A conservative force, let 5x Newton, force in Newton, displaces a particle from a position, I am taking x1 from a position x1 2 meter to another position 4 meter. Then find change in potential energy, delta U. Okay, we have to find delta U, and change in potential energy is negative of work done by conservative force. Integration of work done, this is du integration, and this is U initial, U final. So this is a delta U, U final minus U initial, delta U minus integration of A, displacement is along x-axis, dot. You will follow this formula, f dot dx, this is negative of work done, f dot dx, and limit varies from x1 is 2 meter, x2 is 4 meter. Now you can calculate minus f is 5x into dx, limit varies from 2 meter to 4 meter, and delta U is equal to minus 5 x square by 2, and limit varies from 2 meter to 4 meter, and delta U is equal to minus 5 by 2 minus 5 by 2, and here x square means 4 square minus x square means 2 square. So this is 5 by 2 into 16 minus 4. Then delta U is equal to minus 5 by 2, 16 minus 4 is 12, 6 into 5 minus 30 joule. Two simple questions. Then next question. A conservative force, I think you have perceived it. Okay. A conservative force. Suppose we are taking one-dimensional motion along x-axis. Now let's take two-dimensional motion. A conservative force, FCF. A conservative force, suppose I am taking in space. You may take on plane in space 2x I cap plus 3y square j cap along x-axis, along y-axis. You may take up to this. Again I am adding here 3z square k cap. Displaces a particle from a position from P1. Position is P1. I am giving three-dimensional motion. The coordinates you may take 0, 1 meter, and force in Newton. Okay, 0, 1 meter to another position P2. P1 coordinates, this is x, this is y, this is z, 0, 1 meter and 1 meter. Then another position you may take P2, 2 meter, 3 meter. 2 meter, 3 meter, whatever you may take, this is 3 meter. Then you have to find what is change in potential energy, and in simpler way you may write change in potential energy is negative of integration, negative of work done. I have taken integration because this is total change in potential energy, conservative force dot displacement, but here displacement is in space. I am writing it complete form, you will calculate miles. This is force along x-axis, so what is the complete form? Negative fx dx x1 to x2 plus integration f1 dy y1 to y2 plus integration fz dz integration from limit z1 to z2. Then complete this, you will get your answer, and the integration of fx is, and as you know the expression for force we have discussed in previous lecture, fx I cap fy j cap plus fz k. Here fx is given 2x dx, limit varies from x coordinate varies from 0 to 2 meter, 0 to 2 meter plus integration of fy is 3y square into dy. Then y coordinate varies from 1 meter to 2 meter, 1 meter to 2 meter plus integration of fz is 3z square into dz. The z coordinate varies from 1 meter to 3 meter. Calculate and get your answer. Okay, you may comment me what you have got your answer. Calculate and comment. Very good. You can calculate it easily. This is about some fundamental numericals on potential energy. Okay. Of course, another type of question is there. You will comment me. On chain. You will comment me. Suppose, in previous case we have discussed an uniform chain is overhang. A part of overhang part is L by 5 or L by 10, whatever may be. Suppose an uniform chain of length L, mass M is a line on a quarter circular surface. This is a uniform chain. Total length is L, total mass is M, and the radius of the circular track is R, and this is a quarter circular track, and angle is pi by 2. You know it. Then you have to find what is potential energy. Potential energy of the total part, and here this is datum, this is top position. You have to find total change in potential energy. Just this is easier. Just take a small part. Let this part is dl. This is very small angle, d theta. This total angle is theta. This is radius r. This is also radius r. See, what is total length of the chain? Total length of the chain is pi r by 2 for semicircular length. Total mass is let m. Okay. Length is m, but here length is l is equal to pi r by 2. Total length is on the surface of quarter circular surface. So total length L is equal to pi r by 2 for unit length m by pi r by 2. That's equals to 2m by pi. So this is mass per unit length, means linear mass density, what we have discussed. Then for length dl, this is an elemental length. So 2m by pi r into dl. Then first we have to find potential energy of this elemental section. This is very small because d theta is very small. Then from ground, this is height h. this angle is theta. Then H is equal to r sin theta. This is r cos theta, this is r sin theta, and this is taken as dm. Mass of this part is dm. Then total change in potential energy is m dmg h. Height is h. Now just to calculate d, sorry, this is d. Then to get total change in potential energy, integration of d, dm is 2m by pi r into dl into h. Okay. Then about dl, you see d theta is equal to length of arc is dl and radius is r. As you know, angle is equal to arc length divided by radius, and arc length is equal to r d theta. Okay. Then for dm, mass is dm, and what is dm? You get it 2m by pi r into dl. In place of dl, we may put r d theta, and it will come r get cancelled. 2m by pi into theta, sorry, d theta. So this is the dm. In place of dm, we have calculated this 2m by pi r. In place of dl, let's put r d theta. R get cancelled, and this comes 2m by pi into d theta into 2m by pi into d theta. Okay. Then just put here integration of du, u initial, u final. So this is u final minus u initial, change in potential energy, integration of 2m by pi r. In place of dl, just write r d theta into h. What is h? What is h? H is r sin theta. Then delta u is equal to r get cancelled. So 2mr divided by pi integration of sin theta into d theta. Sin theta theta. See, the total length varies from 0 to pi r by 2. But here you have to take limit in accordance with angle. Here angle is 0. See, if radius vector is turned to this position, then angle is 0, and it is turned to the final position, then total angle is pi by 2. Limit varies from 0 to pi by 2. 90 degree, you know it, 90 degree. And this is equals to 2mr by pi. Sin theta d theta integration is minus cos theta. Limit varies from 0 to 90 degree, pi by 2. And again, I am doing here calculation. Here, delta u is equal to 2mr by pi minus cos 90 minus cos 0. Cos 90 minus cos 0. Then delta u is equal to 2mr by pi minus cos 90 is 0, cos 0 is 1, this is 1, then delta u is equal to 2mr by pi. It is correct or not? Just check it. Just check it. It is correct or not? Correct? Have you done yourself? Have you done by yourself? Yes or no? No. What is wrong with this? What is wrong with this? I have left G. You just see. I left G. This is G. This is G. This is G. And this is G. And this is G. This is G. This is correct. Okay, this is all about today's lecture. In next lecture, we will discuss another beautiful concept. Thanks, my dear children. Thanks.